Electricity. I just want to say thank you for making the last video do pretty well. Like, I didn't expect it to get any views. It was just meant to send to my friends and help them study for science a little bit, but thank you for noticing it, I guess. Anyway, this video is incomplete because my science exam is tomorrow and I still had a million other topics to study for, but if these videos keep doing well, then I'm gonna make a lot next year. Like, I'll make them way before the exam so you can actually study off of them. Anyway, enjoy the video.
Hey guys, if you're here, you probably watched my chemistry exam review. Well, now it's time for electricity. Now, where does electricity like that come from? Well, there are many different places to come from. The sun, water, wind, fossil fuels, coal, and natural gas. There's also nuclear energy, which I can't show because I don't have a nuclear reactor at my house. Or do I? But while some of these kinds of electricity generation are good and renewable, others are bad and non-renewable. Basically, anything that we have an infinite supply of on Earth is renewable energy. Everything that comes from things that we can run out of, like fossil fuels and coal, is non-renewable energy. While you might think renewable energies are completely good with no downsides, they're usually really expensive to set up and pay for in the first place, which a lot of people don't want when they're getting electricity. But while non-renewable resources are cheaper at first, in the long run, they have detrimental effects to the Earth. While things like nuclear energy don't produce any emissions, they do produce a toxic nuclear waste that must be carefully disposed of. So we can see that all types of energy generation do have their benefits and drawbacks, but usually renewable energy is the way to go.
Now let's do a little experiment with two magnets. The front of this magnet is positively charged, and the back of this magnet is positively charged. Let's see what happens when I try to put them together. They repel each other. They do not want to stick together because like charges repel each other. The front of this magnet is negative, and the front of this magnet is positive. See what happens when I bring them together? They go together. They don't come apart. But if I try and put the negative side to the other negative side, it repels. Let's say my fridge is a neutral magnetic charge. Let's take the positive side, it sticks. And let's take the negative side, it also sticks. That's because both negatively charged things and positively charged things are attracted to neutrally charged things.
Now, in terms of static electricity, an insulator traps electrons in one spot, making it have a negative charge. And let's just say this is a conductor. It gives away its electrons and allows them to flow freely into the insulator. So if I rub these two things together, and this one was neutral, now it's positively charged, and this one is now negatively charged.
We can draw this out in a diagram. Wool and this ebonite rod are rubbed together. Most of the electrons from the wool transfer to the ebonite rod. Now the wool has a positive charge, while the ebonite rod has a negative charge. Now let's take this ebonite rod, and let's put it near, but not against, two spheres. They're both metal, they're both conductive, and they're both neutral right now. When we bring the negative rod over, the electrons will leave this first sphere and go to the second one because they're repelling the negative rod. Now, if we move the right sphere away from the left sphere and then take away the rod, the left sphere is left with a positive charge and the right sphere is left with a negative charge. This is charging by induction.
If we do the same thing with a grounded metal sphere, we can take our ebonite rod and we can move it towards the grounded metal sphere. Now, instead of the electrons going to the other metal sphere, since there's not one to go to, the electrons will travel to the ground.
Once the electrons have flowed into the ground and the ebonite rod is taken away, the sphere is left with a positive charge. That is also charging by induction. But how do we know whether the wool or the ebonite rod is going to take the electrons? Well, there's something called the electrostatic scale, and it's basically which one is going to be more attracted to the electrons. And it's basically a scale showing us which one is more likely to hold the electrons. Wool is very low on the scale, meaning that it would rather give away its electrons than get more. The ebonite rod is extremely high on the scale, meaning it is extremely likely that it will take all the electrons. So now we know why my clothes get stuck together in the dryer. But what kind of electricity turns this light switch on? And off. It's current electricity. And current electricity works kind of like a hose. When you turn on the electricity, the electrons will flow through the wire, like water flowing through a hose. Let's turn it on and see. Never mind. Clearly my hose is a bad example. But that brings us to different kinds of circuits. Before I show you how to draw different kinds of circuits, don't look at the spoilers, but here is what everything in a circuit diagram means. A straight line is a wire. A squiggly line is a resistor. A little circle with an X in it is a light bulb. Two dots, with one of them not connecting, is an open switch, but two dots with a line in the middle connecting them is a closed switch. And this is a battery. A series circuit is like a hose. It's a circuit with only one path for the electrons to follow. The electrons go from the negative side of the battery, flow through the circuit, and go back to the positive side of the battery. But they wouldn't in this circuit because of the open switch. A parallel circuit is similar to a series circuit, but a parallel circuit has many different paths for the electrons to flow through. Now, if I were to add another light bulb here, and then I were to break this light bulb, this one would also be broken because the series circuit needs that light bulb to complete the circuit. If one of them broke, both would break. But with this one, in a parallel circuit, if I were to break this light bulb, these two would still be on because they are in their own separate circuits. Even if I were to break this light bulb, this one would still work. Series circuits are like old Christmas lights, where if one bulb broke, all of the rest would break. But now newer Christmas lights are made with parallel circuits, so if one light breaks, all the rest stay the same. Here are a couple of rules for each type of circuit. In a series circuit, the voltage is additive, the current stays the same, and the resistance is also additive.
Meaning if I have two resistors that are both 3 ohms, then my total amount of resistance will be 6. And if I had 2 light bulbs that both took up 3 volts, then my total voltage would also be 6. And because it's only one path, the current would stay the same throughout the entire circuit. And in a parallel circuit, the voltage stays the same. The current is additive. Let's pretend I put a current there. The current is additive, so the total current would be 9. And then the resistance gets a little bit tricky, because if you do, a voltmeter is attached in parallel to the power source. An ammeter is attached in series to, well, an ammeter is connected in series. It should be connected to the conductor and the load. And an ohm meter, you have to make sure that your circuit is disconnected and off, and then you connect it in parallel to the load or the resistor. And remember, when you're calculating different parts of a circuit, voltage equals current times resistance.